Okay.
We will hear Benjamin Canou about OC4MC, Objective Caml for MultiCore, which is also, I think, a Gen Street project from back from the first edition of Gen Street Summer of Code. So I give you the microphone.
Okay, it does not respond. Okay, I think it shut down my computer. Okay. Okay, so is it entire? Yes. So I'm Benjamin Canou. Actually, yes, this is a Gen Street summer project, but I'm not one of the students who worked on it. So the Gen Street work has been done by Mathias Bourgoin and Adrien Jonquet, and has been supervised by Emmanuel Chailloux, Philippe Wong, and myself. So a little timeline for the project. So actually, we should grow the arrow on the left. We had Philippe, Emmanuel, and me a previous experience on modifying the runtime library of OCaml, but in a totally different context. It was making a simpler runtime with another garbage collector that is now used in a critical embedded software for building aircrafts. And so we thought at this time that we were able to modify the runtime and make it MultiCore compatible and add parallel threads the same way. Okay, so for this we started this Gen Street Summer project. Then at the end of the summer project we presented totally bugged implementation. We worked hard, but actually it was very difficult to hack. Then Matthias did his master thesis on the same project, and we were able to release a working version that the Smart Pumpkin release we announced on the Caml list. So in this talk I will explain a little what is the state of concurrency, parallelism, strengths, and so on in OCaml. Then I will explain a little OCaml for MultiCore and the performance. And I finish with the conclusion and how is the state of the things now. So, little to remind you, concurrency, which is right now possible in OCaml, is not parallelism and is not distribution, to make things clear from the start. A program can be concurrent, meaning that you can have several execution flows that execute concurrently. That's very useful for expressing concurrent algorithm, to build asynchronous mechanisms and so on, like asynchronous reading on sockets, these kind of things. This is different from parallelism, which means that you have several execution flows at the same time. Okay, and this is used for speed, and HPC is the acronym for high performance computing. So you know this guy, you do scientific calculus and many matrix multiplication and so on. Okay. So in a concurrent or a parallel system, you have to synchronization, communication, and to work on the same data. eventually. So this can be done by message passing. That's the way we like the things to be done because it's clearer interaction, it's safer, etc. But for certain applications like scientific calculus, scientific computation, we would like a shared memory environment. So there are a lot of approaches to concurrency and parallelism and distribution in OCaml. I cited some. So there is the threads module, which adds concurrency to OCaml. There are distribution with GeoCaml, co-threads. There are several shared memory concurrency abstractions like LWT, like the first threads, and so on. What is now missing is a concurrent system which enables parallelism in shared memory. Okay, and it is deadly missing because it is what the recent cheap SMP architecture, they call MultiCore, gives us today. And it would enable it would allow to write a HPC algorithm in OCaml, and also this is a low-level layer that could enable to write higher-level concurrent mechanisms in shared memory. So, what is the state of threads in OCaml today? So there's this thread module in the standard library. It gives a pthread-like interface. You have the typical POSIX thread mechanisms, join, create, join, and the mutexes and conditions for synchronization. It is only for expressing concurrency, since there's only one thread running at a time. You probably all know this in this room. There's a global lock, a global mutex, which is used for scheduling threads internally in the runtime. And the switch between threads is done on very specific locations in the code. It's done on allocation, or on some synchronization primitives, on explicit thread.yield, and so on. So why is this mutex? Some possibly explanation are first, it is due mainly to memory management. You can just add a thread library and make it work without doing nothing, because there are heap structures and you can just share them in write mode and pray for them to be safe. And it is historical. The thread library has been added after the construction of the original runtime that comes from Caml Lite. So, to sum up in a schema, in green you can see the execution of the program. So you have an arrow representing each thread. So you create a lot of threads, but there is only one execution flow at a time, except for special blocking operation. On each allocation, which are the circles, there's possibly a thread switch, and when an allocation failed, the thread that was performing this allocation performs a GC, and then resumes, possibly giving the control to another thread. Okay? I think the picture is clear, if it was not. So our goal is to implement parallel threads for OCaml. So this was not really planned by INRIA. Although it was really a potential interest for the community, and it was really awaited. No, actually, I made. This is obviously a joke, but actually, when we submitted the summer project, I don't hear a thing. Sorry.
Could you read it?
Yes, okay. So Dr. John Harrop said, sorry, this is the best news since I've heard since OCaml 3.11 made it into testing and batteries went into beta. Okay, this is a real quotation. So at the time, actually, we submitted the JSuite project. There was a little enthusiasm on the Caml list. Finally, we will have parallel threads in OCaml and so on. So actually, we thought it was clearly awaited by the community, and it was actually the same problem in other languages. You know, at the time, Python didn't have parallel threads, and it was the case for many runtimes, and that was the problem at the time. Okay, so what we had to do is to modify the runtime library to clean it up. I mean, to remove some mechanisms that are not compatible with parallel threads, and to design a new one, MultiCore compliant, I mean SMP compliant. It means a new allocator, a new garbage collector, which are MultiCore compliant, and the associated new thread library without the mutex lock. That was a little the way we sold the project to JSuite. They really wanted something, some project that could be reused later or that could be integrated into the upstream distribution. So actually it would be really difficult to integrate, to change the runtime totally with parallel thread and to give to Xavier's team and ask them to integrate it. I think it's not really a possibility. So what we proposed was to do it without modifying at all the compiler and just to bring an alternative runtime. So you compile with the original OCaml opt and you just link it with the alternative runtime and voila, you obtain the parallel threads. Okay, that was a little difficult. Okay, so how we made the runtime reentrant. There are several parts that were not reentrant. For example, the execution context of the language was stored in global variables. So the exception pointer, the stack pointer, so these kind of things. And they were saved and restored on context switch. So you had associated to each thread a structure in which on each thread switch the global variable were saved and restored. So we added a per thread structure, which is now updated in real time. So this is quite difficult because every time you want to change these execution context elements, you have to access this local data. For the C side of the runtime, it's possible to do this with POSIX functions, so it's quite slow. We tried it. For the assembly or kernel part, it's quite more difficult. So what we did on the first approximation was to use the widespread AMD 64 architecture. We modified a little the compiler so it gives us one register back, and we use it to cache the local thread data structure. And so this was really faster. Apart from this execution context, there were other global variables to clean up. So in some parts of the runtime, there are in fact local data which are, we don't really know why, put into global variables. So sometimes it's because there are several functions and the runtime doesn't want to pass the parameters to each function. So we did it back. We added parameters to some function with the local data. We added some fields in the local in the thread local data structure. This kind of things. The real problem was only to identify where these data were in the runtime. And also there are shared data, you know, like shared structures, the graphics window handler, these kind of things, the I/O variables. So for this, that we call non-performance critical, at least at a first glance, we protect it with mutexes, simply. And of course, we had to rewrite the heavily accessed global data, which are the heap structures. So our new memory management, I will first present rapidly the original memory management system. So there are two heaps. The young heap, in which the allocation is very fast. It's actually 2 assembly instructions, one decrementing a pointer, then a test. And if the text succeeds, then it's okay, the allocation is done. There are 3 algorithms. The first to copy on each minor generation the survivors, the alive values to the old heap, and then a quite complicated but very efficient algorithm on the old heaps. As I said earlier, or as Sylvain says, this GC is triggered only on really specific points as the context switch. In fact, it's the points where the roots are known. It means you cannot stop your program anywhere and know what are the alive values in the stacks. So, so you have to stop at very precise moment where you know exactly which values are alive in the stack. To simplify. So we designed a new, which allows parallel execution and accesses in read and write to the heap. So parallel, a fast allocation of small objects. It's almost the same cost. We have the inherited behavior, which are a little more, a little less acceptable now, but I mean we have to stop the execution flow on allocation, and this made us design a stop the world garbage collector, which means that we have to wait for each thread to stop in a valid position. So we have to wait for every thread to allocate before we perform a GC. I will show you a graphical view further. So how do we have a quick allocation? It's quite simple design. Actually, we have a set of small heaps. Every thread can reserve for its own use a small heap. The reservation is protected by a lock. And if it wants to allocate big objects, it allocates it directly in a shared heap with a second global lock. But most of the time, when a thread wants to allocate small objects, it's quite fast and it doesn't require a lock or a write barrier. So the GC phase, the GC is done in 2 kind of phases. The first is flushing the alive value from the small heaps to the old shared heap. Okay, and when the shared heap is full, we perform a big stop and copy algorithm. So we copy all the alive value into a new big shared heap, and we freeze the small heaps. Okay. So that was for the algorithm. Now for the synchronization mechanism. So now the arrows are green at the same time. So actually we have a parallel allocation. You can see parallel execution. And when one thread misses an allocation, so there is no more small heap to reserve, and its own small heap is full. It says to other threads that he wants to perform a GC. Then it has to wait for other thread to perform an allocation, and when all threads are stopped, it performs a GC, and then everyone starts with a new small heap and so on. Okay? So that was the mechanism, that was the design. Now a little bit about performance. I will speak about this Smart Pumpkin edition. Actually, this is the last, we'll say, stable. We have a development release which has sometimes better performance, but it's too crashy, so I won't speak about it. In this section, I will talk about it later. So we can, on good programs, that are written for parallelism. Parallel algorithm, we can have the 8 or approximately 8 factor on a 8 core machine, so it works. It's actually parallel. So typical example like matrix multiplication, like this kind of things. There's a pi calculation approximation in which you randomly put a dot and you count the one in the circle to this kind of stuff, so, which are really easy and really prone to parallelization. So actually there are programs that are slower than the OCaml compiler with the OCaml runtime, standard runtime, sorry. Sometimes way slower. If you look at this KB, it's a benchmark which performs many allocations, string concatenation, exception slide programming, and which triggers GCs really often. Actually, we are with one thread 2 times slower than OCaml, and it's standard runtime. It's quite simple. Our GC is just not as fast. It's a simple stop and copy. We just cannot be as fast, but that's a really difficult program. So actually, the factor is just 2. It's quite promising. But I will explain now. This was for one thread on each side. If you don't change the program, it means there is the exact same number of tasks to execute, but we enable more cores in parallel, so there are the same number of tasks, but twice as more cores, up to 7, and in fact the execution time grows. It's quite simple to explain. There's no magic. The bottleneck is the memory bandwidth, the context switches, and the cache collisions. It's quite simple. In OCaml, you just launch a task, then it ends up. Sometimes the GC refactors the memory, so it all fits in the cache, is very efficient, and so on. Then we start another task, etc., etc. Or if it is executed concurrently, at least a quite important chunk of code is executed before the control is passed to another thread. If you execute the same task in parallel with many cores, of course each one will try to access its memory in parallel, and so at each instruction or approximately every instruction you will have a cache collision, and you will have to pay the cost of memory bandwidth and cache collisions. Okay, so we really can obtain a performance gain, but of course on parallelizable algorithm, OCaml for MultiCore will not take your program. You add a special less dot map, and it's parallel and very efficient. No, that's not the case, and that won't be. So a little conclusion. So yes, it's working. We have parallel threads with the same interface. We have potential very good performance. We can achieve the 8 factor on an 8 core machine, which is not the case for all languages, even now. We really encourage you to test it, please. Actually, the community was very enthusiastic when we launched the project and when we announced the release on the mailing list, before the email changed into a rant about F# performance and this kind of things. But we only received, I will say, less than 10 bug reports or experience reports, so it's a little discouraging, actually. So the Smart Pumpkin edition you can try is restricted to 64-bit 63-bit, sorry, x86 architecture. Actually, we had to modify the compiler because of this caching of the local structure in a register. So you cannot just compile it with libraries in Debian, because you have to recompile all the libraries with the compiler patched. So it's a little difficult to test programs that requires a lot of libraries. It is available as a patch against 3.10, but we have a development version. We have found a way to really more portable way to access thread local data. Actually, it uses really low-level stack mechanism and so on, so it's not yet really debugged, but it works. And it allowed us to port it to macOS 10 and 32-bit architectures, and potentially every architecture. The main problem was the x86 on which you have only a few registers, so you cannot cache data. We ported it to 3.11, and with this method we managed to have less intrusive compiler modification. With a little more work, we think we could link to non-modified libraries. Okay. Thank you.
A question?
I wonder if you think this work is, in some sense, dangerous, because in another 5 years, of course, we'll have very heavily NUMA machines, and I think that SMP might become slightly less relevant. And in fact, we might have wished that we'd written using message passing and forking and so on down the road.
If you look at our way of programming, maybe, but if you look at, scientific computing algorithm, there are, several layers, I mean. So even if we have a different machine, I think we always have this layer in which the smallest is a shared memory with several thread mechanism. It's the case in graphic cards, which enables huge power. The small brick is yet a multi-core with shared memory, even if there's distribution and message passing on a higher level basis. So I think this approach is still important, and it's a bargain, but so maybe on this the future will tell. I mean.
I've got related questions. You know that, for example, I think Intel just release 48 core machine, which is bringing message passing interface inside the solution, the core. In fact, core doesn't almost share nothing, and are sending messages around inside the chip. So it's related to the question, and I ask it again: do you think that shared memory will end by winning the parallelism war?
Actually, I don't know. I think
Okay.
maybe, and I think it's not a good answer and not a good motivation not to do the work. So maybe in the future we will have a good shared memory with threading architectures, and if we are ready, that's better, I think.
There's no problem. I really respect your work because it's really huge. But I'm questioning myself also.
Okay.
In any case, that's interesting. Yes. Yes, it's interesting, of course.
Do the parts that you change in the runtime, like so for the generic comparison and so on, could go into OCaml and maybe allowed to be executed in a blocking section? Does that make sense?
I don't think that the comparison should be executed in blocking section, but this is not the real problem.
Yeah,
the comparison is easily rewritten in a reentrant manner, but
is there a performance loss to?
actually, on comparison, no, or at least it's not measurable.
So maybe that could go into OCaml to make your patch smaller?
Maybe some other parts, like for example in the standard library. For example, if we want to provide an alternative runtime, we cannot patch the standard library, so that's difficult for us. And actually, if the first graphics.open could be made in a blocking section, that would be better. Because now, if you do them in parallel, it opens two windows and then it does funny things. It's not protected. There are other parts we could investigate together if you want. There are other things that could make our patch smaller. For example, there's a compact option in the OCaml compiler, and this compact option is not taken into account for the startup file generated. That was a difficult problem to find. So the compact option explicit calls to the GC and the allocator, but even with this option at link time they are inline code. So maybe that's a small patch that could be integrated. We are still working on this development version in which we really want to minimize the size of the modification to the compiler, and I think when it is ready and when we have something that does not imply a too big performance loss, maybe we'll propose a patch so that our runtime can be better.
Well, actually, you just answered to my question. I was wondering, I didn't get if the development version was meant to be.
Yes, that was one of the main problems. So it's really hard to debug because we write the local data as a fixed stack place, so we do a bit mask continually, and so it's really hard to debug. But when it's ready,
yeah, so that's one of the cool tricks for implementing thread local storage. Damien and I learned it in the Anchor Multimax in 1991 or 2, I guess. Yeah, so on x86 you could also use segment registers, and that's what at least the Windows threading library and the Linux threading libraries do. So maybe you want to investigate that.
yes. Actually, we just we tried to make a really portable approach so that we didn't have much.
Yeah, but well, making sure your stacks are aligned the way you want is not going to be portable anyway. So
it's actually incompatible with Zen. Zen uses the segment register. Zen uses the segment register on 32-bit. Actually, I'm sure there are some Zen people here who actually know how this works much better than I do. But
how can they run Windows or Linux multi-threaded programs?
well, they emulate the ES register or something, and so it causes a huge slowdown when you do that.
Oh, interesting.
Okay.
Did I see that you have speed up bigger than your number of core for your good example? Can you explain it?
I don't think so.
There's something like a speed up of 2.02 for 2 core.
Where?
For the matmult example?
Matmult. Like the 2.02. Yes, there are, if it's not really different, there are many possibilities, like memory behavior and this kind of thing, which can produce this result. Or simply because our watches were not so precise. I don't know.
Yeah, it's even better for I.
Oh yes. So we are really good.
fast.
Okay, thank you.